Hello everyone, I'm Li Chen. Today my topic is a diagnostic study of rainfall evolution during landfalling in a weak tropical cyclone. I'll talk about a relatively weak tropical cyclone case which happened in Shanghai, China in 2018. This tropical cyclone led to severe flooding in the eastern part of China and caused a lot of loss. The presentation will be separated in 5 parts. First is the introduction. Background and abstract will be shown in this part. The second part is the data I used. The third part is the results from the data. The fourth part will be a summary of the presentation, and the future work will be discussed in the last part. First is the introduction part. Tropical cyclones can lead to heavy rainfall, as well as strong winds and storm surge, also cause severe damage, such as flooding and landslides after their landfall. A tropical cyclone can cause heavy rainfall in the Iowa, spiral rain bands, or remote areas. Understanding the structure and evolution of spiral rain bands is of fundamental importance. A previous study analyzed the relationship between the rainfall properties and tropical cyclone intensity change, and found that the axisymmetric Tc rainfall distribution was correlated with tropical cyclone intensity change. The relationship between the asymmetric distribution of tropical cyclone rainfall over the ocean and the environmental vertical wind shear has been extensively studied using observations of lightning and precipitation in many previous studies. Previous studies also pointed out that asymmetric rainfall in a landfalling tropical cyclone may be influenced by not only the environmental vertical wind shear, but also the Tc motion. Non-uniform surface characteristics, such as land sea contrast, coastline, and topography, and mesoscale convective activities. Wang and Wang in 2016 found that the precipitation-induced surface cold pour triggered by cold air intrusion was also important to the rainfall asymmetry in landfalling Tc water in 2013. Yu in 2017 pointed out that among different intensity change categories, rapidly decaying tropical cyclones show the most rapid decrease in both the total rainfall and the axisymmetric rainfall relative to the total rain, and weak storms are likely to produce even larger maximum rain rates than strong storms. It was found in Feng and Shu in 2018 that weak tropical cyclones may have heavy rainfall due to the influence of strong westward vertical wind shear. Then we move to Typhoon Rumbia in 2018. Typhoon Rumbia was a relatively weak tropical cyclone which led to severe flooding. Rumbia made its landfall at 20 o'clock UTC on the 16th of August in Shanghai, China, and moved inland. About 36 hours later, Rumbia tracked northeast. This tropical cyclone turned into extratropical cyclone 1.5 days later and moved into the Bohai Sea. This case is worth studied because only a small part of typhoon made their landfalls to the north of Zhejiang, China. Besides, the rainfall kept increasing after landfalling while the strength was weakening. In this study, I found that the upward motion of the tropical cyclone had a weak wave number 2 structure before landfalling, and then after Rambia made its landfall, only the northern part developed. The results also show that the topography and the vertical wind shear contributed to the asymmetric structure of Rambia. Besides, the large-scale waves in mid-latitude may also have some influence on the evolution of the upward motion and water vapor supply. A high-pressure system and another tropical cyclone system also contributed. The second part is about the data I chose. The High-Resolution European Center for Medium-Range Weather Forecast interim reanalysis data is used in this study. I chose the ERA interim data with resolution of 0.125 latitude and longitude. In this study, I used geo potential height, temperature, specific humidity, zonal, meridional, and vertical components of the wind and divergence from this data in following analysis with 6 hours intervals at 22 pressure levels. The boundary layer height from the surface data from ERA interim data is also used. The precipitation data was merged from the 3 sources of precipitation data. The tropical cyclone best track data was from Shanghai Typhoon Institute of China Meteorological Administration. The third part is the results from the data. The first part of the results is the track and intensity evolution. Figure 1 shows the track of Rambia in solid line and the total rainfall in shading in the unit of millimeter from 6 o'clock on the 16th of August to 0 o'clock on the 20th of August. From this figure, we can see that Rambia made its landfall in Shanghai at about 20 o'clock UTC on the 16th of August and tracked northwest. Rambia reached its maximum intensity and became severe tropical cyclone before landfalling. After about 36 hours, Rambia tracked northeastward instead, and was weakened from tropical storm to tropical depression. Then around 1 day after, Rambia moved over the Bohai Sea and turned into extratropical cyclone. Figure 2 shows the maximum wind evolution in blue line and central pressure evolution in orange line during the period of Rambia. We can see from the figure that, before landfalling, Rambia kept intensifying, and after landfalling, Rambia was weakened. The strength did not decrease rapidly. This may be a favorable condition for heavy rainfall, according to previous studies that slowly decaying tropical cyclones can produce larger rain rates. The second part of the results is the rainfall revolution. Figure 1 also shows the total precipitation in shading during the period of tropical cyclone Rambia. From 6 o'clock UTC on the 14th August to 0 o'clock UTC on the 20th of August, we can see that the rainfall was mainly located to the right side of the track, and two periods which rainfall increased obviously are shown in this figure. The first is after Rambir made its landfall, and the second is after turning its direction. Here, the evolution of rainfall during landfalling will be discussed. Figure 3 shows the 6 hours rainfall evolution and the topography. Figure 3a to 3c are before landfalling, and 3d to 3f are after landfalling. From this panel figure, we can see that before landfalling, there was only a small rainfall center located to the northeast of Rambir and was far from the TC center. Figure 3c shows a small area of precipitation occurred to the southern part of Central and then moved to the northern part in 3D. From figure 3D to 3F, the heavy rainfall developed to the northern part of Central rapidly, while the relatively heavy rainfall to the southern weakened obviously. We can conclude that not only the friction of the land induces the convergent lifting, but also the mountain lifting contributes to the precipitation. Figure 4 is the cape in shading and the environmental vertical wind shear from the radius from 200 to 600 kilometers. This figure shows that before landfalling, the environmental vertical wind shear was southeastward, and after landfalling, it began to turn to northeastward. This has some difference with the result in Feng and Shu in 2018 that weak tropical cyclone may have heavy rainfall due to the influence of strong westward vertical wind shear. However, this panel figure also shows that the vertical wind shear brought low cape to high cape area before landfalling. Which was unfavorable for instability, but the environmental vertical wind shear brought high cape to low cape area after landfalling, which was favorable for the ascending motion. Figure 5 shows the water vapor flux in shading and water vapor flux divergence in contours. The water vapor flux was concentrated in the northern part of Rambir, which indicated that the water vapor supply is more favorable there and can be the source for the heavy rainfall to the north of Rambir.